Is Ryszard Kostecki. Ryszek is also my former PhD student. And the title of the talk, Geometrisation of Quantum Theory Beyond Pure States and Hilbert Spaces.
So I'm a bit disappointed that Jurek doesn't have a story about me, but then I will have a little story at the beginning for kind of warm up the situation. So basically, it is a story about what this talk, where all this topic came from, and like many years ago, when I just started to be a PhD student of Jurek, he was on some conference somewhere, I don't know, in some Western country, like more Western than Poland, and I asked him to buy for me a book. This was Julian Barbour, The End of Time. And he replied to me that he bought this book for me, because it kind of wasn't available at the time to order it from Poland. And he wrote to me, yeah, I bought it for you, but I was very sad about you because next to it there was this red book of Weyl on like curved quantum field theory on curved spacetimes. And kind of, I'm sad that kind of you have chosen this one, not that one. And this was a stimulus to actually like read this red book of Weyl. And from that, I started to be interested in how to make some things more exact in, like when one comes towards quantum gravity from the side of QFT in curved spacetimes and so on and so on. And to those who know the book of Weyl, it's like it poses more questions than answers. But somehow I became interested in the algebraic framework. And from that, kind of under stimulus of Chris Isham, who was kind of a little hidden enemy of Hilbert spaces, and I kind of was suggesting that there might be some sort of, it's nice to see for whether there's some possibility of doing some alternatives to those. I kind of started to investigate the possibility of doing some geometrization beyond Hilbert spaces over the top of algebraic framework. So but maybe I would like tell you more details in it. But somehow it started from this little comment of Jurek on like reading more exact science than popular science. Okay, so I'm now in the place in Poland, but all this story is carried through a few institutions during last 10 years probably. So that's why they are here. Okay, so the actual motivation for the talk, I would like to put there are two quotes. One is from Bogdan Mielnik, he actually recently died, but he was one of the people working in foundations of more general approaches than quantum theory, a convex set approach. And in one of his papers, he gives this very nice analogy that somehow quantum mechanics, as opposed to GR, seems to be very monotonous in its inner structural complexity. And basically, you have just, whether you look at projective spaces or even just look at block spheres, it's very structurally similar, and there is like no such variety of the inner structure comparable to GR. And the question he poses there is like, is it possible to actually extend beyond this linear framework in some reasonable way, in a way that quantum theory would be more resembling the inner structural complexity of GR-type theories, and thus, if this would be possible, like whether it would be more reasonable to sort of gravitize or generalize quantum theory instead of quantizing gravity. And this is one way of putting it, as it's in the quote, but it's actually like similar idea appears in the paper of Abay and his PhD student Troy, and it's also the idea that it's a paper on geometrization, on Kähler geometrization of pure state quantum mechanics. And there is some sort of just thought in passing that, written in passing, that maybe this type of geometrization is still some sort of like an analog of Minkowski type description GR, and we are missing this more global, more complex curve space-time perspective for QM. So this is like a motivation, and now I'm going for more mathematical stuff. So basically, I will quickly tell you like how the Kähler space-based geometrization of quantum mechanics of pure states looks like, because this would be like a departuring point for dealing with geometries over density matrices. And like practically all or almost all what I will be telling you later is actually like to be formulated, and it's formulated at the level of normal states over W-star algebras, and it requires a lot of Banach space-based analysis. But in order to make it like more accessible and clear, I will phrase most of it in terms of density matrices, just to make it like, you know, skip the functionalistic aspect more for the sake of presentation of geometric ideas. Okay, so like many people in different moments discovered part of this framework. There are like some names that are some papers that seem to be one of the most important, but with no attitude towards the completeness of the bibliography here. But basically, the idea is that if you take Hilbert space and you take the scalar product of it, it defines Riemannian structure and symplectic structure, where the tangent space of the Hilbert space is just Hilbert space, in the sense that like it's you look at this as a Banach space, Banach manifold modeled on its own, and there's also like complex structure defined by just I mean the square root of -1, and the nice thing is that it's not only that you have those geometric objects, but everything what is out there in the postulates of quantum mechanics can be reformulated in terms of those geometric structures. So, but actually, like, the essential reformulation is happening with the phase space, which is on the next slide, but it's easier to start understanding from the full Hilbert space. And so, like the first thing is to see that vector fields are that this quantum mechanical observables, which means like self-adjoint operators acting on vectors, they actually defined killing vector fields, and the Schrödinger equation is just Hamilton equation in terms of those vector fields. And then instead of thinking in terms of expectation value of linear operators, I can just consider functions, real valued functions on the space. And also there is a nice feature that although there is like a symplectic structure, there is also a way of thinking that Poisson brackets are actually directly defined by the commutator, which becomes relevant for density matrices, because in case of density matrices there would be no longer a symplectic structure available, by this trick of coadjoint induction of Poisson structure will remain. Okay, so, but this is what happens for the Hilbert space, but in order to like get to this, what is, for example, Aschecker and Schilling, they call it a quantum phase space. And it's actually this name appears in various places. The phase, the projective Hilbert space, one projects this those structures on the subspace of normalized states, with tangent space still being a Hilbert space, but now you have there's like the one extra degree of freedom, which actually is responsible for appearance of U1 connection, which is basically something that is like this underdetermination associated with this constraint of normalization. And but the other properties remain. In particular, this induce metric on this on the projective Hilbert space is Fubini's 2D metric, and there's also a nice relationship between the U1 connection and the symplectic form. The nice thing is that, like, also on this projective Hilbert space, it's very clear that there is some the relationship between the metric part of geometry and the measurement part of the quantum mechanics is like clearly exhibited. So, like, in order to describe this part of quantum dynamics that is not due to unitary evolution, because unitary evolution is described by killing Hamiltonian vector fields, but the part that's associated to vector reduction due to measurement, whether it's degenerate or non-degenerate, it's in any case. It's actually described by projectional geodesics, and the transition probability associated with the projection onto this or other vector is expressed by the formula that's purely geometric. This is geodesic distance of Fubini's 2D metric. So somehow, like, all those parts of quantum kinematics and dynamics, both statistical and causal, are becoming re-expressed in terms of geometric structure. However, here we have just pure states, and the question is, like, what we can do with density matrices, and yeah. So now I will tell first about global theory, and then I try to localize it for what does it mean. I will tell later. So the main object of consideration would be subsets of trace class operators, which means basically not necessarily normalized density matrices. However, this is just for convenience of simplicity of presentation. Essentially, everywhere here I have in mind positive parts of preduals of double-star algebras, but it really doesn't matter here. The main objects, there is no longer a symplectic structure available. However, what happens here is that one can introduce naturally the Poisson structure, actually the Poisson structure. And the other thing that there is no, one can introduce various metrics, but it appears that the more natural object to use to describe the statistical part of the theory is relative entropy, or actually the class of relative entropies. Okay, so I will first tell you about how the Poisson structure works. This work is mostly due to Pavel Bona, and then for density matrices, and it was generalized to W-star algebras by Ogievich and Ratiu in 2003. But basically, the idea is to consider self-adjoint part of trace class operators. So you can think of it that it's like with operators, you might have positive operators or self-adjoint ones. The same you can do with states. It's like because it's basically Banach space, so you can also like cut off some part of this linear space, and it's real Banach space, so it can be also considered a Banach manifold model on its own. So the tangent spaces to it are just itself. And then you can do the trick of what I told you before with the Poisson brackets being induced from commutators. So here it turns out that, well, if the tangent space is the self-adjoint trace class operators, the Banach dual to it are self-adjoint operators, and at the same time, so it's at the same time the object that is like they are operators. These are also one forms, and so basically you can have like completely meaningfully read this equation as in terms of operators, but also in terms of differential geometric objects, and and then the story goes. So the nice thing is that there is this well-defined integrability of vector fields despite of the lack of a symplectic structure. And this is the more general theory in which it is contained is our Banach Lie Poisson manifolds, but I will not go into it. The main thing is that at the end of the day, what one gets is that for any smooth function, smooth real-valued function on the quantum states, on the density matrices, one gets the generalized von Neumann equation. So, which in general, its solutions are not. It's not a group. The solution satisfies some cocyclic relationship. However, in the case when the functions when the Hamiltonian function is given just by expectation value, you get ordinary von Neumann equation. So this is like a sort of, basically it's like nonlinear generalization of von Neumann type evolution, which is nice because it holds for arbitrary density matrices in any dimension and W-star algebras. And all of this is just induced from the Lie structure of self-adjoint part of the algebra. So this is the Poisson part. Now I'm going to and corresponding to the causal description, I'm going to speak of the geometric part associated with the statistical side of the theory. And to start, I would speak of relative entropies. There is some terminological issue, so. And it's kind of, I think it's unresolvable because in principle, this thing here, the beginning, this trace rho log rho with minus, it's von Neumann entropy if it would be with minus. So in order to make it consistent, the relative entropy should be having minus here. However, by unknown reason, people in literature started to call such functionals relative entropy at a certain point. Other people call those functionals information divergences, but it doesn't have any relationship with divergence as we know it in differential geometry, so it's like a confusion of the notion. People sometimes call it non-symmetric distances, but it's even adds confusion. So I will call those D's relative entropies just for the sake of simplicity here, but I don't think it's a consistent terminology. So there are various things, so this is like an example of basic, this is like a omega key relative entropy, which is relativization of von Neumann entropy and quantum version of Kullback-Leibler entropy. But there are like various other functionals that could be as well considered and are considered in the quantum information theoretic literature for various purposes. And basically, the properties, if one tries to identify what kind of properties would a generic relative entropy possess in order to make sense of it for any purpose, or like some purpose at least, it's basically something like this. So it's like a two-point function of quantum states that is valued in 0 to infinity, and it at least has to satisfy such a property. So it's like 0 when if and only if those 2 points are the same. And additional properties like lower semi-continuity, convexity, and so on would be added given what we want to have from it, which will follow immediately. But basically, the starting point is just to have spaces of quantum states equipped with such functionals. Okay, this what can be done with those functionals is, and like the purpose why I'm introducing them is that one can do constraint maximization of relative entropies. So basically, and consider this as a generator of mapping on the state spaces, of mappings on state spaces. So basically, like the prescriptions take some functional and take some constraint set. Take some quantum state psi and take some constraint set of quantum states onto which you want to project this Q, and then find the minimal value of this relative entropy, or in the standard terminology it would be maximal value if the entropy would be with minus, but here it's without minus, so it's minimal value. And if such minimum exists and is unique, then this would be the outcome state. This would be the projected state. Naturally, like so far it's an ansatz. The question is like, I mean, the necessity is in specification of conditions for existence and uniqueness of this prescription. Okay, but like at least for a few, there are already examples for which it works. So if one takes Hilbert-Schmidt distance squared, then and takes closed convex subsets of Hilbert-Schmidt space, then basically this type of projection is the same as projection operators within the Hilbert-Schmidt space. Hilbert-Schmidt space is basically like finite dimensional, or maybe not even finite dimensional, but it's a discrete version of GNS construction. So for any one of you who like GNS, it's already there. And the other example is just perturbing the state by the expectation value. It's also such type of projection. Also, the result is unique. Why I'm even considering it? So the main reason to consider it is the following. It basically stems from thinking of quantum measurement not as like material thing that happens with the material quantum state out there, but actually like a prescription for learning or updating the state of belief, state of knowledge, and so on. So like quantum state in this prescription is just belief, is considered to be a container of information. And there are like some people who are proposing developing this view and so on. And basically, according to this view, at its like elementary formulation, the elementary prescription for quantum measurement, like Luder's rules and so on, Luder's rules are basically generalization of state vector reduction to density matrices. So it's like, so it's basically like state vector reduction, but without necessity of having pure states. And like people who were starting quantum Bayesianism in various flavors, they were thinking of it, oh, this should be interpreted as Bayes' Laplace rule somehow, and they were like proposing the ways. And so some people in probability theory community, a bit in like Bayesian inference community and maximum entropy, people, they have shown that Bayes' Laplace rule and also many other rules of probabilistic state update can be derived from constraint relative maximum constraint relative entropy maximization. And so the nice thing is that actually this is also the case for the quantum measurement prescriptions, variety of them. It's true for Luder's rules, it's true for some more general rules, it's also true for the partial trace. And I'm not claiming yet that it's like true for anything you can extract from POVMs, but POVMs are also derived from very specific presumptions. So it's still open how much of everything what POVMs can do can be got from it, received from it. But at least in the statistical part, so without unitary part of POVMs. But basically, it's clear that at least it gives certain alternative paradigmatic description of large class of description of quantum measurement beyond standard vector reduction. So the question is now naturally, okay, we can generate description of state change due to. So like the just for people who are not very accustomed with the Bayesian information theoretic perspective, the point here is that like if quantum state is considered to be just a container of users' knowledge, it's not that there is a material change in the system described in the quantum state that happens when we do the measurement, but basically whoever describes the system by the quantum state receives some type of information. This information is used by this person to change his description, which is the quantum state. So like the quantum state is a property of the user of the formalism, not a thing out there. And so those constraint sets are understood as some data that are describing the measurements. But it's interpretation anyways, but I just would like to avoid some confusions. Okay, so the question is, okay, we can do those projective measurements, and it's nice, but how much time do I have actually?
Altogether 12 minutes, but including the questions.
Okay, I would then do the coarse-grained presentation. So, so the question is like, is it possible to guarantee existence and uniqueness of those projections to actually like restrict this like ansatz to something very specific? And the answer, yes, it is possible. And there is a class of relative entropies for which we can guarantee existence and uniqueness of those projections. And these are so-called Bregman relative entropies. And the nice thing is they can, all of them satisfy very interesting geometric property. And at least in commutative case, then they actually can be characterized by this property. And this property is so-called generalized Pythagorean theorem. So to make, so basically, and for any relative entropy between 2 points, it actually can be additively split by means of projection on some affine subset. And in the case of Hilbert spaces, it's when you think of it, this is just a projection operator on some linear subspace or affine subspace. This is something that maybe some of you at least know, like as a property that you can orthogonally combine. It's basically like Euclidean version of Pythagorean theorem upgraded to Hilbert spaces. But the nice thing is that those functionals, Bregman relative entropies, which satisfy this, they may be arbitrary and nonlinear. So like the appearance of one of the most fundamental things from Euclidean and Hilbertian geometry for this class of relative entropies seems to be very, very interesting. Okay, so this is like some sort of like ansatz that one can do some aspect. One can go to hunt for the general geometry of density matrices and more general algebraic states using those two geometric structures that I presented, both for kinematics and dynamics. But there is something still missing, and like in Kählerian geometry, we had both statistical and causal aspects described locally, and those entropic projections are non-local, and there is something missing. So the question is, okay, this is like just what I'm saying, that like inference can be described by entropic projection. Causality, we have Hamiltonian flows with nonlinear Hamiltonian functions, and we can combine like P of VMs, at least in some representation, can be understood as combination of measurements, like projection measurement and partial trace with unitary evolutions. Here we also can combine, propose certain ansatz. So this part is differential geometric. This part is convex optimization. So it's like nice. It would be nice to have like some sort of geometric side to it. And this is what I mean by local theory. So I will just quickly review a few geometric structures that are relevant here. So we all know Riemannian geometry. There is a nice generalization of Riemannian geometry that satisfies very similar characteristic equation, just you have two connections and the parallel transport is done for one vector along, like with respect to one connection, and for the second vector is done with respect to the other connection. Those connections have to be torsion-free. And so this is like, sometimes it's called conjugate geometry. This is something what is more known to geometers doing affine differential geometry. Like, there are many references for like Udo Simon and so on. Like, it's also, there is a book of Nomizu, and I don't remember whom by this, that also contains this. But anyways, the thing is that like there is such a geometry, and if those connections are not only torsion-free but also flat, then the resulting geometry has nice feature that there are two affine coordinate systems for which the metric actually can be represented in Hessian form, which in turn is very nice because the Hessian geometry, there is like one-to-one correspondence between this and Codazzi geometries with flat connection. So this is like Codazzi geometry is, I mean, the Codazzi structure is like more general. You can put various tensors there, but here I mean like Codazzi structure with Riemannian metric and a flat torsion-free connection. And and at the end there is like one more geometry I want to recall. It's like Weyl geometry. This is something what Weyl used in his upgrade of Einstein since 1919, like to 1920 something. And it's the nice thing is that Codazzi geometries determine Weyl geometry. There's also determination in other direction, and under specific condition there's actually equivalence. But I will not go into it. I just want to tell you that like for those who have some interest in Weyl geometries, like the Hessian geometries that are here, they always generate some specific Weyl geometry uniquely, and under some condition actually they're equivalent. So the nice thing here is that basically when one considers relative entropies that are smooth and have positive definite second order derivatives, like second order Hessian, actually like the Taylor expansion of those relative entropies gives Riemannian metric and two affine connections that are Nordensen geometry. And if one takes this Taylor expansion for the Bregman relative entropies, which I've been like recalling earlier, then it actually gives Hessian geometries or equivalently Codazzi structures. So basically, like if you go with Bregman relative entropies, and that I've been talking before, you actually always you get into local. I mean, if they are like smooth, you get into local Codazzi structure on state spaces. So and associated Weyl geometry. Example is here. It's a very simple example. I'm sorry, that without calculation, but basically the idea is that if you take normalized states and you take relative entropy, like the standard Umegaki relative entropy, then this is how the derived the Riemannian metric and parallel transports of the connection look like. So, and there are like many more. The nice thing is basically that when you have this localization of the relative entropies into the local Hessian structure, you can equivalently describe entropic projection by means of geodesic projection, and this is super cool. So in the sense that like basically like here is the picture. So like instead of just maximizing relative entropy with respect to this constraint Q and getting the point P as the unique optimizer, and you don't know much more, here you actually know that you are projecting when you go into this local description, like when you expand it into the derivatives. Actually, it's a projection along the geodesics of one of those connections on the surface that has to be affine, and in the convex global formulation, it was just affinity, linear affinity, but in the differential geometric setting, it's actually affinity with respect to this other geodesic structure. Nice. So basically, at the end, the story is that one can localize the statistical part, those entropic projections, and think of this purely statistical evolution as something that's localized as sort of free falls along geodesics of those connections. And okay, so there are like some things that are to be done, but I shouldn't extend 1 minute. So there are like the nice thing that would be let's make it the last message here. So basically, the nice thing would be to take this local description arising from Banach Lie Poisson structure and to connect it with those entropic projection localized to geodesic free falls. But the problem is that both live on different smooth manifold structures over the same sets of points, but the structure is different. So actually, like making addition of two forms, like it doesn't make sense mathematically, and it's like an upper problem that I'm kind of trying to find a solution of. There are like other open problems, and maybe I will leave this slide because there are like some return back to GR as what can be used from this thing. I can, if someone will ask me, I will explain it, but I don't want to exceed the time.
Other questions or comments? Thomas.
I have a very basic question. Maybe you said it, but but then I missed it. So it seems that there's a very natural way to extend the pure state case to the case of density matrices by using the Hilbert-Schmidt norm. Mm-hmm. So is this what you're doing, or this is much more than?
So basically, like it's a special case of everything what I've been saying. The thing is that this just corresponds to a particular embedding that I've been presenting. This corresponds basically, there was this D1/2 that was here as the relative entropy, and here, and it was carried. I could carry it Fourier systematically. So basically, it's a special case.
Okay.
Absolutely. Yes.
Thanks.
If there are no more questions or comments, let us thank again.